Okay, so welcome back. Yeah, there's slight technical issues. My laptop's keyboard's not working, and YouTube was being fussy about the stream. So earlier, now it says it's fine. So, but if you hear or if you see any noticeable issues with the stream quality, then let me know in the chat. So anyway. Yeah, someone else has asked for a playlist before, so I'll either do that or I'll add to the descriptions. I still haven't organized all of our lectures into a playlist. I'll do that actually later today. That way, over the weekend, if you're referring to everything, it'll be in some nice playlist. So, how hard do I say the exam is? I mean, it's it's like roughly on the level of the homework problem. So I don't think it's that hard. Um, the exam itself will be posted later today. I won't give a exact time, but it will be sometime in the afternoon, and I'll make an announcement when I post it. So you don't have to be you know, waiting by your computer for it to drop. You can just, you can calmly wait. You're gonna have plenty of time, so you don't have to worry. You don't have to send me a million emails about when is the exam going to be posted. Did I miss the exam? I will let you know when it's posted. Okay. So, one thing I wanted to tidy up and finish, and just because it's a really nice way of practicing some of the stuff that we did, I wanted to do an example of computing the curvature and torsion of two very convenient curves for us. So we already know what the curvature of a circle is. We computed that last time, right? And so just reminding you, this is what the torsion of a curve is. Okay, so we'll compute the torsion of a circle, and then I'm going to compute the curvature and torsion of a curve that is similar in a lot of ways to the circle, and show you what it is that's going on here. So first things first, so recall that if C is the curve parameterized by, say, big R cosine t I plus big R sine t j, this circle of radius r with t. Remember, don't make the mistake of writing a parameterization for a curve and not including where the parameters live. You're not done until you've included where your parameters live. Okay, so say you have a parameterization like this for your curve C. So if this is what you have going on, we actually already computed the curvature of this and found it to be 1 over r, right? It was constant. Okay, so this is an example of a curve, a constant curvature. But it was, inversely, right? It was 1 over r, meaning that, as the radius of the circle got larger, this, so as you chose curves that had, circles that had larger and larger radius, this curvature is smaller and smaller, closer to 0. Now, according to what I said last time, that curvature for plane curves determines the curve. What this means is that actually, if you have a curve with constant curvature that is non-zero, okay, or maybe I should include that case. So if you have a curve that is has constant curvature, there are two cases. Either the constant curvature is 0, or it's some positive non-zero constant, right? So in the event that it's 0, that curve must be a part of a line. Okay, and in the event that it is non-zero, in the event that it's positive, that curve must be a part of a circle. Okay, because as I said, since the curvature determines the curve for a plane curve, that's required. Once you know the curvature, then you've nailed down what the curve is. Now that's not true for space curves, and this example will show that. So let's remind ourselves how we computed this. So we computed r prime. So r prime of t, just going through quickly here, this is minus big R sine t I plus big R cosine t j. Okay, and then if I take the length of this, of course, this is square root of, it's going to ultimately be sine squared t plus cosine squared t. So this is, this is r squared sine squared t plus r squared cosine squared t. So it's going to be square root of r squared, or r, right? Okay. So that my tangent vector for this thing, I know we've worked through this example many, many times, but so that my tangent vector is going to be r prime divided by the length of r prime. So it's going to be minus sine t I plus cosine t j, right? So I've divided through by the constant r. Okay, and then from that, length of t prime is minus, or sorry, not length of t prime, just t prime itself, is minus cosine t I plus sine t j. Okay, sorry, minus, this is a minus. I did that before too, so this is a minus. So then the length of t prime of t is going to be square root of cosine squared t plus sine squared t. Okay, so for my purposes of finding this curvature, actually, it wouldn't have even mattered if I'd screwed the sign up. But of course, if I was trying to find the normal vector, I need that sign to be right for that component to be right. This is 1. Okay. And so my curvature, right, kappa of t is the length of t prime of t over the length of r prime of t. So this is 1 over r. We did this last time. Okay. Okay, so, of course, if I wanted to write the normal vector for this curve, I could have done that. That's, that would just be this t prime of t divided by this length, which is 1, so it would just be t prime. Okay. Now, I want to compute the torsion of this thing. So let me remind you what the torsion is. So if you have a curve, okay, the torsion, first of all, the torsion's only defined when the curvature is non-zero everywhere. Well, for any fixed radius r, my curvature is 1 over r. That's always positive, right? That's always greater than 0. And so I have this fact. So my torsion is perfectly well defined for this curve. The torsion is r prime cross r double prime dotted with r triple prime divided by the length of r prime cross r double prime squared. Okay, so let's compute the things we need here. So we have r prime, we need r double prime. So what is r double prime here? So this is minus r cosine t I minus r sine t j. All right, so that's r double prime. And I need r triple prime as well. So r triple prime is minus r cosine t. I take the derivative of that. Derivative of cosine t is minus sine, so this becomes r sine t I. Okay. And then the derivative of this slot becomes minus, this is minus r cosine t j. Okay. Okay, did I do that right? I think so. I think everything's right there. Okay. All right, so now I want to compute r prime cross r double prime. So you see now why I want to compute this torsion. Let me bring it back on the screen real quick. So here's the torsion. The reason I want to compute this is it gives me an excuse to do cross products as an example. Dot products, I don't think anybody has any issues with that. Length, squaring the length, it gives me an excuse to do all these things as practice. And so, so what is r prime cross r double prime? What is that? Well, just remind you, here's r prime, and here is r double prime. And so let's write our normal cross product. So we're crossing vector valued functions here, right? Which is something that I can't remember if we did. We might have done like a single example of doing this for vector valued functions. It works the exact same way as for vectors. you're doing this pointwise, right? So you're just doing this pointwise. Okay, so I need r prime in the first slot, so that's minus r sine t plus r cosine t is in the second slot. But k, we have come across a conundrum here, right? What is our conundrum here? Well, this curve is, of course, a plane curve, right? So this curve is a plane curve, and as a plane curve, there's no k component, right? But our cross product was always defined as a cross product between two vectors in space. So how do I remedy this? Well, if I'm thinking about this being my circle in the plane, the xy plane, I can think of the xy plane as sitting inside space, and it sits inside space at height 0, so I could really think of this as having a slot here, 0k, right? And so I can do that with all of these things, because of course as I'm taking derivatives of 0, I still get 0. And so all this is still fine. Okay, so thinking about that, what do you notice here? Well, this slot is 0, of course. R double prime, I get minus R cosine t minus R sine t and 0. Okay. Well, of course, because of this column of zeros in my cross product, what does that mean? This makes my life easy in one sense, because for the I and j slots, right, I'm going to have 0 minus 0 and 0 minus 0. So this is going to be 0i plus 0j. So the only slot that's not going to be 0 just on its face is k, or is the k slot. So covering that up, I get minus r sine t times minus r sine t, so I get r squared sine squared t. Okay, minus r cosine t, or r cosine t times minus r cosine t, so this is plus r squared cosine squared t times k. Okay, and so that's what the cross product of this is. Of course, I can simplify this a little bit. So this is 0i plus 0j. If I factor out an r squared there, what do I get? I factor out an r squared. I'm left with sine squared t plus cosine squared t, which is 1. So this is plus r squared k. Okay. But now I'm dotting this, right, so I can compute the length of this, of course. There's no need. Because once I write this out, so of course the length of this is square root of 0 squared plus 0 squared plus r squared squared. So the length of this is square root of r to the 4th. So this is r squared. This doesn't matter because when I dot this, if I'm computing the torsion, right, this is r prime cross r double prime dotted with r triple prime over the length of r prime cross r double prime squared. But when I dot these two, what do I get? So r prime cross r double prime dotted with r triple prime. Let's bring r triple prime back onto screen. R triple prime is r sine ti minus r cosine tj plus 0k. But r prime cross r double prime is 0, 0, r squared. So what is that dot product? All right, what's the dot product of this vector and this vector? 0. And so the torsion is 0 over like r to the 4th, whatever, we don't care, it's just 0. Okay, so the torsion of the circle is 0. Okay, now the question is, Is that right? What is that how it should be? What's going on here? Okay. Well, let's compute the curvature and torsion of the helix. Okay, so let us compute the curvature and torsion of the circular helix. So recall, the circular helix is a curve C. One example of a circular helix has parameterization cosine t I plus sine t j plus t k, right? Okay, where t, we'll say t goes like, it's just one arc of this circular helix. Okay. All right, so here's my circular helix. First, I want to compute the curvature, and then I want to compute the torsion. Okay, so in order to compute the curvature, just recall, right, kappa of t is length of t prime of t over length of r prime of t. Right, this is the curvature. Okay, so let's see what's going on here. Let's compute r prime first of all. So if I compute r prime here, this is minus sine t I plus cosine t j plus 1 times k. I'm just taking the derivative of each slot. Okay. All right. So then I need to find the length of r prime of t so that I can actually write out what t prime is. So what's the length of r prime of t? Well, I'm taking the square root of minus sine t squared, so that's sine squared t, plus cosine t squared, so that's plus cosine squared t, plus 1 squared. But sine squared t plus cosine squared t is 1. 1 squared is 1, so this is 1 plus 1 underneath the radical, so this is square root of 2. Right, as we've seen before. Okay, and so my tangent vector, t of t, which of course is r prime of t over the length of r prime of t. This is, here's r prime. I'm dividing it by root 2. So this is, maybe I'll write it here because I have more room. So this is minus 1 over root 2 sine t I plus 1 over root 2 cosine t j plus 1 over root 2 k. All right, there's my tangent vector. Okay. Now I need to compute t prime and the length of t prime. Okay, so t prime of t is I'm taking the derivative of each term here. So this is minus 1 over root 2 cosine t I minus 1 over root 2 sine t j, and the derivative of 1 over root 2 is 0 because it's just a constant. Okay, and so now I take the length here. The length of t prime t is square root of minus 1 over root 2 cosine t all squared is, of course, 1/2 cosine squared t plus minus 1 over root 2 sine t all squared is 1/2 sine squared t plus 0 squared. Right, is the last component. Okay. And so, what is this? What is the length here? So this is square root of 1/2 times cosine squared t plus sine squared t. Remember, this is 1, so this is just 1 over root 2. Okay. So, what is my curvature for the circular helix? Well, it is 1 over root 2 divided by length of r prime, which is root 2, which is 1 over root 2 times root 2, so it's 1/2. Now, of course, I could have written down a circular helix of a different radius here, but for this circular helix, its curvature is 1/2. What is important to know, or to notice here, I should say. So the curvature of the circular helix in space has the same curvature as what other curve in space? So I'll wait for chat. So here's my question. We just computed the curvature of the circular helix that I wrote down. Its curvature was 1/2. What other space curve has curvature 1/2? So note this circular helix with curvature, again constant, has the same curvature everywhere as another curve in space. What is another curve that has this exact same curvature? The circle with radius 2, exactly. The circle with radius 2. Exactly. Because the curvature of a circle is 1 over r, where r is the radius, right? And so we've just shown that there is an example of a curve, right, that has the exact same curvature as the circle, but it's certainly not a circle, right? The circular helix is definitely a different curve than the circle, but they have the same curvature. Okay, so this is the difference between plane curves and space curves for that thing that I said. So in the plane, for a plane curve, the curvature totally determines the curve. Once you know the curvature, then that nails down exactly what the curve has to be. But for space curves, that's not the case. So if I told you, consider a curve in space with curvature 1/2, you actually wouldn't know what I was talking about, because we have the circular helix has curvature 1/2, and we also have a circle of radius 2 in any plane located wherever you want. That's also another example, okay, of a curve that has radius 2, and there's no motion I can do. I can't take a piece of a circular helix, right, and move it onto a curve, right? Any piece, no matter how small I take, and move it onto a circle. Any piece, no matter how small I take, is going to be moving up and up and up and up and up, right? Even just a little bit, it's going to be moving up and up and up, whereas a circle does not move up at all. It is totally flat. Okay, it lies in a plane. In fact, as we'll see, I'm going to compute the torsion of this circular helix, and then I'm going to tell you what it is the torsion's actually computing here. Okay, and so it turns out that for space curves, curvature is not enough. You need curvature plus torsion to tell you exactly what the curve is. So it's the curvature plus the torsion that determines the curve for space curves. So let's compute the torsion. Okay, so let's compute the torsion of the circular helix. So, as we saw already, let's just copy here. R prime is minus sine t I plus cosine t j plus 1k. Okay, so R prime of t is minus sine t I plus cosine t j plus 1 times k. Okay, so what else do I need? I need to compute R double prime of t. So that is, so R double prime is minus cosine t I minus sine t j plus 0k, right? Derivative of 1 is 0. And I also need to compute R triple prime, of course. So R triple prime is minus sine t, so this is sine t I minus cosine t j plus 0. Okay. All right. And now for the torsion, I have to compute the cross product of r prime and r double prime. So r prime of t cross r double prime of t is what? So this is my usual cross product notation, ijk. Second row is r prime, so this is minus sine t cosine t 1. So we're not as lucky as we were in the case of the circle. R double prime is minus cosine t minus sine t 0. Okay, so let's see what is going on here in each slot. So I have something times I. What is that something? So I'm blocking out this first row now. So I have cosine t times 0 minus sine t times 1. So I have sine t. Then I have minus something times j. Now I'm blocking out the middle column. So this is minus sine t times 0 minus cosine t times 1. So that's cosine t times j plus something times k. Now I'm blocking out this row. I have minus sine t times minus sine t, so that's sine squared t, minus cosine t times cosine t, so that's minus cosine squared t. Well, that worked out perfectly because this is sine squared t plus cosine squared t. So what is this? This is sine t I minus cosine t j plus 1. Okay. Okay. All right. Now, I need to compute the length of this. That's one of the other things that, so just to remind you, the torsion of the curve is r prime cross r double prime dotted with r triple prime, all divided by the length of r prime cross r double prime squared. Okay, that's torsion. So the length of r prime cross r double prime, I didn't write the prime there, is square root of sine squared t plus cosine squared t plus 1 squared. So this is actually not so bad. This is square root of, this is 1, so this is square root of 2. And I need to square that, of course, which I will take care of later. So that thing squared is just 2. All right. So now I need to dot r triple prime and this cross product. Let me leave that on the top of the page here. Okay. And so r prime cross r double prime dotted with r triple prime is, so this is sine t times sine t plus minus cosine t times minus cosine t plus 0 times 1, or 1 times 0, however you want to write that. And so what do I get? Oh, I get our favorite. Again, sine squared t plus cosine squared t. So 1. Okay. And so what do I do now? My torsion is r prime cross r double prime dotted with r triple prime divided by the length of r prime cross r double prime squared. So this is 1 over, this length is square root of 2, so that square root of 2 squared is 2. The torsion is 1/2. So the circular helix and the circle of radius 2 have the same curvature everywhere. but the circular helix has torsion 1/2, and the circle has torsion 0. Okay. So intuitively, what is torsion telling you? So torsion is like curvature was measuring the rate of turning of the tangent vector. So the curvature is telling you how fast the tangent vector is turning. Okay. Torsion is telling you to what extent your curve bends out of a plane. Okay. That's tau. Yeah, that's the Greek letter tau. So this is tau. Okay. That's the Greek letter tau. Okay. So, yeah, lowercase tau. So the torsion is telling you the degree to which a circle or a curve in space bends out of a plane. And so if a curve is entirely contained in a plane, so imagine that in space you go and you draw a curve like this. Okay, that's a piece of a curve in space. But notice that this curve is entirely contained in this piece of paper. All right, so if I take that curve and then I move this piece of paper however I want to, now this is a curve in space, but I can totally fit this curve in the plane. So now take the paper away, just leave the curve behind, sitting there floating in space. If I slid the paper back onto the curve, I can fit that curve entirely in this plane. This curve has curvature whatever. It's going to change at different points, right? It's going to have less curvature here and more curvature here. But the point is that its torsion is 0 because it's entirely contained in a plane. So it turns out that that the letter for curvature is kappa. So this is kappa. Okay. Just be happy that, I'm not using lowercase c. Right? C is rough. Uppercase c is easy, but lowercase c is not as good. I'll tell you all a story since you're talking about the Greek letters here. So lowercase c looks like this. That's actually a bad version of it. There. This is a very good version of lowercase c here. Let me bring it closer so you can see what it looks like. Oh, it's having issues. There we go. This is lowercase c. So if you're curious what Greek letter I'm saying, this is c. Okay. This is not the same as like chi, right? So lowercase chi is this. All right, so this is c. What does uppercase c look like? Uppercase c looks like this. So this is uppercase c. Okay, it's 3 disconnected lines like this. Okay. So there was a very famous mathematician who also was a famous international ping pong player, I think. Anyway, but this guy wrote a bunch of really famous texts. I don't like most of the texts that he wrote, but they are nonetheless very famous and they're used as the textbook for several graduate courses in math the world over. So this guy was a really, really famous mathematician, and apparently he was very, very anal about how notation was written, like during talks, right? And that's not that surprising. Mathematicians have the best notation, right? We're a lot more clean in our notation than like physicists or something. And so this guy was well known to interrupt a talk if he felt like the speaker was saying something or was writing something on the board that wasn't that clear, or his notation was bad. He would interrupt the talk. He would scream, "Your notation sucks!" Okay, so he was well known to do this, and people kind of tolerated him because he was famous and because it was funny. So anyway, and this was years ago. This is a long time ago. So anyway, he was in attendance to a talk, and a guy who was giving a talk knew that this guy who would scream obscenities at people for using bad notation, was in the audience, and he wanted to specifically elicit this reaction in him. Okay. So the Brandon, the guy was Serge Lang, is the name of the guy who would scream about notation. So anyway, so this mathematician who's given a talk knew that he was in the audience, wanted to elicit this reaction intentionally. And so what he did was the following. So there's something that we're not going to do in this course, obviously. If you have a complex number, so if you have a complex number x plus iy, where I is square root of negative 1, right? So I is the imaginary unit. If you have a complex number, and I'll call it z here. Oh, I didn't mean to write it like that. Here, let me rewrite it on a fresh piece of paper. So if you have a complex number, z, so that's x plus iy. I is imaginary unit. That's not, why do I keep writing? See, I'm doing Calc 3 stuff too much. I keep writing bars on top of my eyes. So anyway, you have a complex number like this. The complex conjugate of a complex number, you write that by putting a bar over it. So you have z with a bar over it. Okay, and so what is the complex conjugate? All it does is it takes x plus iy and changes it to x minus iy. That's it. This is called the complex conjugate. Okay, and to complex conjugate anything, you put a bar over it. And that's true for complex valued functions as well. So if I have a function f of a complex variable, then I can talk about the complex conjugate of that function. I put a bar over it, okay? And just like we do, right, when I have a bunch of functions, f of t, h of u, h of xy, when you have functions that have arguments, that have variables you're plugging in, when you're writing that a lot, you don't always want to just keep writing this stupid variable. It takes too long. So you'll suppress the notation. You'll just write f. You'll just write h, g. Or with us, with our parameterization, when I wrote the formula for torsion, right, and so on, blah, 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 I didn't include the t, even though all these are functions of t, right? So this is technically what is here. Right? And you do that because it just takes too long to write out all these things. And it's understood, you're taking derivatives. It's understood that they depend on t, typically, right? Blah, blah, blah. Okay. And so you suppress the notation. So then what happens if you have a function like this and you suppress notation and you write its complex conjugate? Well, you have f with a bar over it, okay? Well, what if you take a function f and you divide it by its complex conjugate and you're suppressing notation here? So then you have f divided by f bar. Okay. All right, that's fine. Nothing wrong with that. Then this is a quantity that you want to consider a lot. You want to take a function divided by its complex conjugate, no problem. Okay, but what if instead of f you use as letter for your function, you get more creative and you use a Greek letter, right? Let's say you use the capital Greek letter Kasai, right? Or Kasi if we're being more proper. So Kasi in place of f here, divided by its complex conjugate. Well, here's Kasi divided by Kasi bar. There it is. Right. There's Kasi divided by Kasi bar. This is my this is my expression for my function. Right? Okay. And so the guy did this. The guy wrote this on the board, and apparently the mathematician in question almost had a heart attack when he saw this expression on the board. Okay. This is related to, back in the olden days of the internet, you're playing some online game, and in the online game, the only way to communicate with someone was to literally type out their name. Okay. So you had to type, /tell or /whisper and then the person's username, right? So then what you do, if you're a really cool guy like I am, what you do is you make your username this. You make your username a bunch of lowercase l's, lowercase i's, and what is even better is if you throw some ones in there. And what's even better is if this first one is like a capital I. right? Now, if you are in some, if you're playing some game that allows you to have capital letters in the middle of your name, well, then some of these can be capital I's, right? And so the beauty of this is, of course, you're playing the game, and then you see someone that you want to make angry on the internet, and you say, hey, you suck, right? You're terrible. You're an idiot, whatever, right? And then you sit there and you wait. And eventually there will be a reply, but in the time it takes for them to reply to you, you get to chuckle as you know that they are over and over again typing and then getting it wrong, right? It's like, user does not exist. And they're like, oh my God. And they're like sitting there counting, okay, how many I's, how many L's, right? Just so they can respond to you, and hate on you. It's great, right? It's great. Making people angry on the internet is good. Good stuff. So, of course, all your friends, if you use this as your username, will call you barcode. That is what people tend to do. Anyway. So that's that. That's that story. As I was saying about torsion, the deal is that it's measuring the degree to which a curve curves out of a plane. So if a curve has torsion 0, that means it's entirely contained in some plane. Okay. All right. So there's like a good 10 minutes of class left. So if there are general questions, I'll answer those for a little bit. So let me know. I will be paying attention to chat, and so that I'm not sitting here completely silent. I'll put on some tunes. Let's see here. Yeah, this is a good one. Yeah, here we go. All right. So I will be here. Type questions in chat, okay? And I will be here for at least another like 10 minutes. Okay, so let's see. I have a few questions here. So one, can you explain again that does it mean by having torsion? Oh, if you have torsion equal to 0, it means your curve is entirely contained in some plane. That's what it means. And so torsion non-zero, or what torsion is actually measuring, is the amount that a curve curves out of a plane. Let's see here. Which should I prefer, email or Elm's message? Email, please. Elm's message is terrible, unfortunately. So if some of you have sent me Elm's messages and I didn't get back to you, it's because it gets lost in the problem is the format, that the way that Elm sends it, when it sends you a message, it sends me an email anyway. The problem is that it sends me a poorly formatted email that is hard to respond to. So yeah, don't send me an Elm's message. Send me an email instead. That's much better. Let's see here. Can we email your TAs with questions when the exam is open? You can email us with questions, but we won't be that helpful with specific exam questions. Like, unless there's some. So one, I don't think there's going to be any. There's not going to be any issues of like like what is this problem saying or anything like that. So I mean, yes, if there's a question like that, if there's some problem that where I've just written gibberish, then you could get an answer about that problem. But in general, you will be left to your own devices for exam problems. But you can ask questions about similar problems, right? Okay. Let's see here. How many questions are going to be on the exam? Well, here's a philosophical thing, right? So, what is the difference between a question or an exam with 20 questions, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way down to 20. And what is the difference between that and an exam that has 5 questions, but each question has 4 unrelated parts? Or possibly somewhat related parts. Is there a distinction to be made there? Because the best answer otherwise would just be to say that there will be enough problems. There will be problems that cover everything. Let's see here. 12.5, number 7. Let me actually look at the 12.5, number 7. Well, that is an example of if you are good at doing some early, so if you're good at doing some nice early simplifications, then it's not so bad. So yeah, that's the key. That's the key to number 7 is doing basically make sure your tangent vector is as simple as possible. Let's see. Number 8 on 12.6, is that the hyperbolic sine and cosine one? You don't have to worry. I'm not going to put hyperbolic sine or cosine on the exam itself. So if your main concern is like the dealing with hyperbolic sine and cosine, you don't have to worry about that. So the reason I chose to do torsion is not covered like at all typically in Calc 3. The reason I wanted to do it was we did curvature, and you see how curvature, if you can compute tangent normal vectors, the curvature is a free thing. So the curvature is really easy to compute. I mean, it's easier to compute than you already have the info for it. You just literally write it down. The reason I want to do torsion is it's a more interesting way of doing practice on all of the stuff that came before. Because the main thing that we didn't see today that you should remember is how to write equations of lines in space, how to write equations of planes in space. But of course, once you understand, oh, here's the form those things take, and here's exactly the pieces of info I need to be able to write that, then it's not so bad, right? It's just a matter of figuring out how to get those pieces, which usually, will involve crossing something or dotting some things together. Let's see. Does it make a difference if I have all my components on one numerator for t? Let's see here. Will the final exam be a synchronous exam? No, it'll be the same format. Final exam will be the same format as this one. So the final exam, I will post it, and you'll have a couple days to do it, and then you'll upload it, and that'll be that. Will I post homework solutions? No, I didn't plan on it. Although most of the things or many of the things I should say, can be computed, via, you could use some computer algebra thing to check your answers, like a Wolfram Alpha or something could check answers to some of these things. But no, I tried to give a mix of some even and odd on the homework. I think the last homework I skewed probably a little bit too. I can't remember if I might have given too many even problems. I don't know, but most of the, there's answers to the odd problems in the textbook, and the textbook has a lot of, you can expect a lot of those sorts of questions. So there's a reason why you might say, wait, like why do we keep like taking the curvature, or why do we keep trying to find the curvature in all these quantities of curves that are like pretty simple? Like if you looked at that list, the curves involved are not super complicated, and there's a lot of repetition. The reason for that is you saw how in the case of the parabola, just y equals x squared, right? Computing tangent normal vectors is actually kind of complicated. So there's actually not that many nice curves that I could give you, that wouldn't take many, many pages of calculation. So that's the reason why there's a lot of repetition of things here. Are we allowed to use online resources like similar practice problems as long as we're not consulting other people? Yeah, you can use online resources. The whole point though is all your work has to be your own, and if you want anything graded, then it should be on the paper, right? So, but you can't collaborate with other students, so it's just you. My TA records the discussions, but I can't find them under Zoom. Any idea? Well, no, I think so let's see here. Are they posted in a link to an announcement, or are they posted on the actual Zoom? Because let me look at the so well, I'm not sure. There's nothing listed under the cloud recordings on Elms. So maybe you should one, you can email your TA and ask them where the recordings are posted. I didn't see them under the Zoom tab. Previous meetings. But this doesn't actually allow you to see them. Okay, yeah, I don't know. Yeah, it doesn't seem like they're on it. At least I don't see them anywhere here. So yeah, you may want to ask your TA about that. I'll ask too. I'll see what's going on. Oh, Panopto, yeah. Oh, but do I even? Let's see here. Yeah, I mean, I actually don't have a tab for this class for that, so I don't know. I mean, it could be that your TA doesn't actually know that you're not able to see them. So actually, talk to your TA about that. I don't know where where they're posting them, or whether or not they're being posted to Elms at all. If they are, then I may need to change something in the course to make them viewable again. All recordings from Zooms are under Panopto recordings for all my classes. Yeah, the thing is that I haven't actually set up I haven't set up that tab yet. So let me, Panopto recordings. There it is. Okay. Oh, I don't understand. Yeah, anyway, I'll have to work on this. I'll have to work on this later. I don't see. I do not see what's going on here at the moment, so I would have to deal with this later if I need to. But I mean, let your TA know, because it could be that they don't know that actually you're not able to access it. So let your TA know, and if I'm missing something, then I can work on fixing that. How do you tell the difference between smooth parameterization and piecewise smooth parameterization? Derek, the difference is that if it is piecewise smooth, that means there is some problem point that would have to be eliminated or would have to be ignored. You would have to split the curve. So, for instance, if you have something, if you have a curve like this versus a curve like this is smooth. There's no problem point. Here, there's a problem point right there, and so we would have to split this curve into two smooth pieces. All right, so notice if we got rid of that problem point, then C1 is a curve that is totally smooth, and we don't care about what happens at the endpoints. That's why it doesn't matter. This point doesn't matter anymore. And C sub 2 is also perfectly smooth. So the entire curve is not smooth, but you can break it into smooth pieces. That's what piecewise smooth means. It's if r prime is 0, not just undefined. Being undefined is a problem too, but it's r prime being the 0 vector is an issue. Okay. All right, everyone. I think I gotta head out because I have a meeting with some students here in a little bit. But anyway, so I will post the exam this afternoon, and I'll send out an announcement when I do. All right. So otherwise, I will see you all on Monday.